Okay, so the main things that I want you guys to look at from section 4.2 before our next class are just the basic definition of a binomial experiment and the notation that goes along with it. These are the things that we're going to be using to find binomial probabilities and even to find mean, variance, and standard deviation. Those things we'll talk about next class, but if you have this initial information, then it's going to make that a little bit easier for you when we go through it in class. All right, so in 4.1, we talked about general discrete probability distributions, right, where we just have a table of information, possible outcomes, and probabilities for each one. The binomial distribution is a specific discrete probability distribution. So what that means is that certain conditions have to be met in order for you to be able to use the binomial distribution, okay? And that's what we're going to start with defining here. I've listed the 4 conditions for you, and as we define these 4 conditions, we're also going to define the notation that's going to be used here. If you're going to use the binomial distribution, you always have to know the values of n, p, q, and x, okay? So let's start with n. In a binomial experiment, n represents the total number of trials. Now, in a binomial experiment, a trial, that's just whatever is going to be occurring a set number of times in your experiment. So if you're going to interview 10 people, then the number of trials is 10. All right. If you're going to flip a coin 15 times, then the number of trials is 15. And so what the first part of the binomial distribution says is you must ensure that you have a fixed number of trials. That just means you have to know up front how many times your experiment is going to be done. It can't be open-ended, okay? And so when you define that, you label the number of trials as a value of n, okay? So that's the first thing you want to look for. The second thing you want to do is ensure you can define a success in your experiment. All right. Now, this is a discrete distribution. That means the random variable is going to be counting something. And specifically in a binomial experiment, the random variable x counts the number of successes in that experiment. All right, so when you're trying to figure out what a success is, look at whatever you're counting and define that as your success. All right, for example, maybe you're going to interview people and you're going to count the number of people who say yes to a certain survey question. All right, in that case, a success is that a person says yes to the question. Maybe you're going to flip a coin 15 times and you want to count the number of times you get heads on the coin. In that case, a success is getting heads on the coin. Okay, so again, a success is whatever it is you're interested in counting. Now, when you look at that success, right, whatever it is you're interested in counting, you need to be able to calculate the probability of that success, and you need to ensure that it stays the same for every single trial that you run. All right, that's a big one, and we'll look at that in some of our examples in just a minute. All right, and then lastly, you need to make sure that you're only interested in 2 outcomes, that everything can be grouped as either a success or a failure. All right, for example, if you're interested in counting the number of people who answer yes to the survey question, then everybody else would have to be classified as a failure. That might be responses of no, or not sure, or maybe, or I don't know, but they would all have to be grouped together as a failure because in a binomial, you can only be interested in 2 possible outcomes. All right, now you also want to be able to talk about that probability as well. So we label Q as the probability of a failure, which again is just essentially that a success does not occur. All right, now, because success and failure here are complements, all right, only one of those can occur, and one or the other has to occur. You either have a success or you have a failure. You can always determine the value of Q, the probability of failure, by taking the value of P and just subtracting it from 1. That's the rule of complementary events. All right, so let's take a quick little example here, and let's just run through kind of how we would determine if we have a binomial experiment, and how we would label the values of n, p, q, and x. All right, so in this example, let's say we are going to select 3 cards from a standard deck of 52 total cards. All right, now what I'm interested in this experiment, all right, my random variable x, I'm going to count the number of kings that are selected. Okay, so if I'm questioning, okay, is this a binomial experiment, the first thing I'm going to do is define a success. All right, a success is whatever I'm interested in counting. So a success would be when I select a card, I get a king. All right, now based on that, I'm going to kind of run through my properties and I'm going to try to define the values of n, p, q, and x. All right, n represents the total number of trials. I have to know how many times I'm going to run this particular experiment, right? How many people am I going to interview? How many times am I going to flip the coin? In this case, how many cards total am I going to select? Okay, so right there I can see, I know this experiment's going to run 3 times. I'm going to look at what happens when I select 3 individual cards. Okay, so we're good there. I've defined a success, right, as selecting a king. So now I need to make sure that I can define P, which is the probability of that success. And I have to make sure it's not going to change. Okay, so let's think about that on the first card, right? We're not given the probability here. We're going to have to calculate it, but we can do that, right? Just event over total. The first card that I select, right, probability is event over total. I've got 52 cards to choose from. All right, the event, right, the success here is that I select a king. All right, so in a standard deck of cards, there are 4 suits. You have a king in each one of those 4 suits. There's a king of hearts, king of diamonds, king of spades, and king of clubs. That means there are 4 ways that I can select a king. Probability is event divided by total. So my probability of success is 0.077 if I round that to 3 decimal places. Now, in order for this to be a binomial, I have to make sure that is not going to change. So what I do is I think about the next card. All right, so let's say we've selected the first card, right? It's a king, all right, that's done. When we go back for a second card, notice there's not going to be 4 kings in there. There's only going to be 3. There's not going to be 52 total cards. There's only going to be 51. That's a different probability, all right? That's a value that's changing, and that's not okay for the binomial, right? For the binomial, the probability of success has to stay the same for every trial. So as it stands right now, this would not work, right? I would have to stop right here and say, you know what, this is not binomial because that probability is not staying the same, all right? However, if I just change the wording up here a little bit, in order to use a binomial when you're dealing with items being selected, you just have to state that the selections are going to be made with replacement. If it's without replacement, it won't work. It's not binomial. But if it's done with replacement, then that probability is going to stay the same. There'll always be 4 kings. There'll always be 52 total because you're putting it back every time the selection is made. Okay, so if the selection is done with replacement, we've now checked the number of trials. We've now calculated the value of P, so we'll keep going. Now, everything else should be grouped together as a failure. All right, anything that's not a king would be considered a failure. So in order to find the value of Q, all I have to do is take P and subtract it from 1. And that tells me the probability of failure is 0.923. That's the chance that I don't get a king. All right, so at this point, we've checked 3 out of the 4 properties off here. Last thing we need to do is make sure that we can understand the possible values of x. Now remember, x counts the number of successes, in this case the number of kings. If I'm going to select 3 cards, my possibilities here for x, I could have 0 of them that are kings. I could get 1 king, 2 kings, or 3 kings, but that's it. Right? Can't get more than 3 kings because I'm only selecting 3 total cards. And just so you know, in general, when you're listing possible values of a binomial experiment, it will always be the counts from 0 up to whatever your value of n is, because you can't go above the total number of trials. Okay, so this is what I'm going to do anytime I'm asked, is something a binomial experiment, or if I'm just thinking about using the binomial distribution, right? I want to check these before I do. And I have to be able to identify n, p, q, and x, or I'm not going to be able to use the formulas that go along with the binomial distribution. Okay, so let's run through this with one more example, a situation where the probability is actually given. We don't have to calculate it. And then we'll continue this when we meet for our next class. All right. So again, all I want us to do is look at this second example, check the properties for a binomial experiment, and then label the values of n, p, q, and x if what we have is indeed binomial. All right. So I read through all the information here. 39% of adults think the government should help fight childhood obesity. I'm going to randomly select 6 U.S. adults. And then notice what I'm going to be interested in counting here. All right, this will tell me a success, so I always want to look for that first. The number of U.S. adults who think the government should help fight childhood obesity. So I'm going to go ahead right here, and I'm going to label a success. All right, a success here would be a person who thinks the government should help fight childhood obesity. All right, that's a success because that's what I'm looking to count. Okay, so based on that, the first thing I'm going to look for is my fixed number of trials. All right, I'm interested in how many people think the government should help fight childhood obesity. So I need to know how many people am I going to talk to. All right, that's my fixed number of trials. I'm going to select 6 adults, so n here is equal to 6. Okay, so we're good there. Now I need p, right? P is the probability of success. All right, well, a success here again is that the person thinks the government should do this. And so if you notice right at the beginning, you were given a percentage that corresponds to this group. And a percentage is a probability, right? We talk about, going back and forth from one to the next. So I'm being told right here at the beginning that the probability that a person will think the government should do this, that's my success, is equal to 0.39. So I don't have to calculate it in this case. It's right there. All right, now everybody else would be grouped together as a failure. All right, so to find Q, I'm just going to subtract 1 minus P. All right, that's basically if 39% of people think the government should do this, then 61% of people think the government should not do this. All right, and also notice there's nothing in this problem to make me think that that probability is going to change. All right, and again, that's important because I want to make sure that the value of P stays the same with every trial. All right, so we've checked off N and P and Q. The last thing we need to do is think about the possible values of X. All right, again, if we're counting how many people think the government should do this, there could be nobody. There could be one person who says yes, two people who say yes, and this can only go up to 6, right? Because I'm only talking to 6 people. So possible values of X are the counts from 0 up to 6. Okay, so we're going to pick up from here in class, and we're going to use technology a great deal here. So we're going to look at using technology to find probabilities, and then we'll also look at finding mean, variance, and standard deviation. But these are all things that are going to be based off of identifying a binomial experiment and looking at values of N, P, Q, and X. Okay, so what I'd like you to do before class is I'd like you to go into your 4.2 practice and just look at, I think there's only 2 or 3, but look at questions that ask you, is this a binomial experiment? All right, and for those questions, right, see if you can answer yes or no, and look at identifying the values of N, P, Q, and X, because if you can do that, then the rest of this is going to be pretty straightforward, just going to be plugging in the values of N, P, Q, and X.